All right, recording is rolling. It is Tuesday, November 1st, and we're going to focus today on these chapter 10, 11 puzzles from your book. Okay. If you guys have this page, although now this is a page I gave to you guys quite a while back. I always like to give you guys stuff plenty of time in advance so that you can always look ahead and see what questions are coming up and say, okay, yeah, see how it's next. Okay. Now, number of students haven't had this earlier today, so I handed out all my extra copies. This is my very last copy, just one of these into just to read and teach by. Okay, so I will go print some more of these after school, so I'll make some more hard copies. But I'll tell you guys what, if you want access to this, since you guys have laptops too, right? Let me show you guys exactly where to find this on Google Classroom. So they present screen 2. All right, let me refresh this. I'm sure it's going to be here. Here. Right. Okay. All right, so physics honors, right, classwork, right. We're right here. Scroll down, and here, energy assignment, chapter 10, 11. Okay, so one of these, I tell you these time problems, is 5 from one chapter, 5 from another, right? And this is the actual page then pull off, right? So I copied a bunch of problems from your book. As usual, I copied like a ton of problems and then just assigned you a handful of them, just like we normally do. Right. So that, if you want to see some other problems, and guys, it's got lots of other ones there. Right, so that file is on Google Classroom. Okay, let's switch back over here. Okay. Now, before I jump into these, I'll tell you guys what we're doing tomorrow, just so you'll have a day to think about it. Right, so guys, remember yesterday I gave you this page. Now, who does not have this page? Maybe what's on this page? Does anybody not have this page? Okay. Oh, all right. Okay. So, remember on the back side are a bunch of conceptual questions. We might do a Kahoot on these. So we might have time later this week, maybe. And then on the front side here, a couple of labs. Now, yesterday we did this one with the pendulum swinging and said, what's the maximum speed of the pendulum at the bottom? So we did that. You guys calculated it, measured it. Said, oh yeah, those are totally the same. Okay. And then tomorrow, we're going to break out those ball launchers that we were using back in projectile days. Right? You remember doing like projectile lab? Now, the old question used to just be, what's the speed of the launcher? Right? How fast is the launcher launching the ball? Okay, now that didn't depend on the mass of the ball, but that aside. Okay. And tomorrow we're going to do that, but take it one more step and figure out, well, what is the spring constant of the spring? It's like as you put the ball in, like click, 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 you have to click it in. Like the more you compress it, like you're putting energy into the spring, like spring potential energy, and pow, it's going to launch the ball and it's going to land at some distance. Okay, so let me sort of guide you guys through the thought process so that tomorrow you'll have a day to think about this. Okay, so if you know how far the ball goes and how much time, that could tell you the launch speed, couldn't it? So you say, okay, here's the horizontal distance it went. It was going some horizontal speed across, right? And some amount of time. If you did the distance divided by the time of fall, that could tell you the launch speed. Okay. Now you could sit there with a stopwatch and calculate or measure the time, but the problem with that is that that's probably not a very accurate way to get the fall time. A more accurate way would be to calculate the fall time based on this fall height. Right? If you guys go back to h equals 1/2 gt squared and calculate the fall time. Okay, so that measured distance divided by the calculated fall time can tell you the launch speed. Okay? Now that's sort of where, as far as we went back in the day for projectile motion. Okay? And what we're going to do tomorrow is do that, so do all the stuff, but also go the extra step saying, all right, now we're going to set up a conservation of energy. Let me zoom away in here. And the conservation of energy, you guys know, it always goes from some point A to some point B. But those points are going to be right next to each other. Okay. Point A is going to be the ball is spring loaded inside the launcher, and point B is going to be right as it's exiting the barrel. Okay. So that you go from spring potential energy to all kinetic energy. Now, if you're thinking, wait, isn't there like a mix of kinetic and also gravitational potential because it's some height? Yeah, if you wanted to like treat this as your point B down here, maybe you could do something like that. But that's not what we're doing. We're going from point A inside the barrel to point B, like right when it's leaving the barrel. So you could define this as height 0. It goes from all spring potential to all kinetic. Okay, guys got that? Okay. So you got 1/2 kx squared turns into 1/2 mv squared, where v you will have calculated, based on projectile physics. Okay. And then so that 1/2 kx squared, you solve for k because that's the point of this lab. It's going to be, can you figure out what that spring constant is? Okay. You will have had to compress it, right? Like smash it some amount. Isn't that what X is gonna be, like the compression distance? I labeled that right here, spring compression X. Okay. Suppose you smashed it, I forget exactly what it is, it's like a few centimeters. Let's just make something up, suppose it's like 3 centimeters. Are you guys gonna put 3 under this column for 3 centimeters? No, what number are you gonna write? 0.03, right? Because that would be how many meters it is, right? 0.03, 3 centimeters, 0.03. They may not be the actual compression, it might be, I forget. It's something kind of like that, though. Okay. All right, so that's going to be tomorrow's adventure. We'll save that for then. All right, so let's take the rest of today and do as many of these problems as we can from chapter 10 and 11. All right, so we won't be able to do all of them. There's going to be 2 or 3 left over. We'll save for another day, but as far as we can. All right, so chapter 10, energy, work, and simple machines. First one I assigned to you guys was number 52, so let's just do that right now. Third floor of a house is 8 meters above street level. That sounds about right, right? Because if every story is maybe a little bit shy of 3 meters. I'm out of extra copies, but it's on Google Classroom, and also I'm gonna print some after school today. Okay, so sounds about right, right? 8 meters for 3 stories. How much work is needed to move a 150 kilogram fridge to the 3rd floor? Okay, so we're gonna lift it up. Notice they told us the mass of the mass of the refrigerator, not its weight, right? So some of these problems they tell us the mass of the object. Some of these problems they tell us the weight. So okay, make sure you keep track of what's what. Okay. So 52 from chapter 10. Yeah. Okay. Yeah. So I'm gonna say the work you do lifting it is equal to. Right? Now there's maybe a couple of perspectives you could take on this. Right? You could do work as force times distance, and that's the definition, right? Okay. So we're lifting the fridge up some distance, and the distance is like the height it moves, so we can just multiply those together. Okay. Alternatively, couldn't you say that the work you do lifting the fridge is equal to the potential energy that you give it by the end? Okay. So like the force lifting it would be equal to its weight, which is like mg, and the distance you lift it is equal to, well, it's like a height change because you're moving it up. Okay. So these 2 formulas could both handle this question, couldn't they? Okay. They're kind of the same idea. So I'm going to say the weight of the fridge, which is, there's its weight, mg, okay. And the distance moved is, well, I'll say distance here, but that could just be its height, right? The work is equal to mgh. Is that right? Okay. And so the mass of the fridge was given as 150 kilograms. The gravity field, so it's right in there, gravity field. Let's assume we're on Earth. It's the only place I know where fridges are. 10 meters per second squared. And the height change, 8 meters.
Are there not fridges in the ISS or something?
Actually, maybe, but no,
I still
no height changes.
They have dried space food, so maybe not.
Yeah, that's a good question. I wonder if they have a fridge up there. So maybe. All right, so 150 by 10 by 8. I'm looking at 12,000 joules. I could call that like 12 kilojoules. Okay, so those are the 2 good answers. Toby, if you did like 10 meters per second squared, what would happen if you plug in 9.8 meters per second squared for gravity? You get like 11,760 joules. So that could be a valid answer too, right? It's like 98% of this. Okay. All right, so those are all good answers. Okay, you guys good? Okay, number 66, sled. We got Diego pulling a 4.5 kilogram sled across level snow at the force of 225 newtons at 35 degrees above the horizontal. If the sled moves a distance of 65.7 meters, how much work did Diego do? Okay. Now, I would not have assigned this to you guys if I had caught that there's kind of a major problem with the setup. There's something in the numbers, but let's just go ahead and solve this and then see if you guys can figure out by the time we're wrapping up this problem. There's a huge mistake and something about the way they gave us the numbers, but we can still solve this up to a certain point. Okay, so 66 sled. Okay. Now, definitely like the premise of this question though, because where's, oh, here we go. Because the force and the distance are not parallel to each other. See, like lifting the fridge, we were lifting straight up and it was moving straight up. Okay. But with the sled, it's like pulling off on an angle, but the sled is like moving forward. So we need some version of work is force dot distance. But you guys remember force dot distance is the same thing as the magnitude of the force times the magnitude of the distance times the cosine of the angle between those, right? It's one way to interpret that. Another way to interpret that is like, it's just the components that are parallel to each other that are all in the same direction. Okay. And actually, I'm going to rearrange this because there's a certain way I like to think of this. I'm going to take this cosine theta and slide it in here next to the force. It's going to be the cosine component of the force times the distance moved, like that. Okay. And the way I like think, reason I like think of that is like, here's your sled. Here's the horizontal, which is the direction it actually moves in. Okay. Here's your force, the pulling force, which they told us was 225 newtons. Okay. Here's the angle is 35 degrees above the horizontal. Okay. So you guys see if you take that 225 Newton force and split it into components, that force is partially pulling the sled forward and partially pulling the sled up. Okay. And we only care about the forward part. Right? That's the only part that's actually doing anything. And isn't that F cosine theta? Right. That's why I moved the F cosine theta together, because that is the component of the force that's actually moving the sled. Right. So we got 225 newtons cosine of 35 degrees. Okay, like that. What is 225 cosine 35 degrees? That's like 184.3 newtons. 184.3 newtons. Okay. So there's only 184 newtons actually moving the sled forward. That's what all this stuff is. Okay. So 225 newtons cosine 35 degrees. Okay. Now it still moves a distance of whatever they said. Was that 65.3 meters? 65.3 meters. That. Okay. So we got 184.3 newtons moving 65.3 meters. Newtons times meters, that'll give us joules of work done on the sled. So that times 5.3. I'm looking at 12,000 and some joules. Okay. Now this 035 part, that's way too precise. I don't actually know those digits. Those are not significant, right? Because they only gave us what, 2 or 3 significant digits. Right? So maybe the best I can say is about 12 kilojoules, or like maybe 12.0. I might know that 0 maybe, but not really the 35. Okay. Guys got that? Okay. Questions so far? All right. Now, there's other ways that we could have gone with this question. They left out a bunch of details, right? They could have said that the sled moves across at constant velocity. And if they said that, then I would say, yeah, sure, Diego is putting 12 kilojoules of work into the sled moving it. But the friction between the snow and the sled is doing negative 12 kilojoules on the sled so that it doesn't actually speed up, right? It's not going up any hills or anything even, right? Or they could have said maybe some portion of this, or maybe all of it, is translated into kinetic energy, like speeding up the sled. So it's like accelerating, right? They were ambiguous. They didn't really say one way or another, right? But before I started writing any of this stuff, I told you that there's like some weird problem with this, right? And it involves the one number that we didn't actually use, which is the mass of the sled. You guys see the mass of the sled? They said it's 4.5 kilograms. Yeah, okay. If I were writing this textbook, I would have said, told everyone, go back and change that number, because there's something wrong with 4.5 kilograms. Okay, that's what's wrong with having a 4.5 kilogram sled with this set of numbers.
It would go really fast.
Okay, yeah, might speed up crazy fast. Okay, let's maybe there's friction going against it. Ooh, speaking of friction, isn't friction coefficient of friction times the normal force? Right, maybe some coefficient of friction between the snow and the sled, right? But ooh, normal force. Okay. Hey guys, if this sled has a mass of 4.5 kilograms, how much does it weigh in newtons about? 45 newtons of weight. 45 newtons of weight. Right. If Diego is pulling partially up, right, then this upward component is like alleviating from that normal force, right? But it better not be more than the weight of the sled. Otherwise, wouldn't you be like pulling the sled off the ground? Right. So this component better not be more than 45 newtons, right? Because 4.5 kilogram sled weighs 45 newtons, right? ooh, let's check this out. What is 225 newtons times, how do I get this component? 225 times what? Sine of 35 degrees. Isn't that true? Sine 35 degrees, right? Now, as long as this is less than 45 newtons, it's okay. Just the sled, the normal force being alleviated. But say 129 newtons, it's way more than the weight of the sled. So he's definitely jerking the sled off the ground. Okay. Sure. All right. So yeah, unless there's like a heavy load in the sled or something, then it'd be all right. All right. So we overthought that one a little bit. Number 67, escalator. We got Salon has a mass of 52 kilograms. She rides up the escalator at Ocean Park in Hong Kong. This is the world's longest escalator with a length of 227 meters and an average inclination of 31 degrees. How much work does the escalator do at lifting her up? Okay. So there's a couple of ways to approach and solve this one. And I'll take you guys through both of the ways. Yeah, it's usually good to have multiple methods to solve things. All right, let's get a picture going. So we've got like the level ground, all right, and then we got this escalator at a 31-degree angle. Pick her up here. Right, there's gonna be, I bet there's gonna be like some height change. I call that H. Okay. And there's a length of 227. What's it? Yeah, 227 meters. Like that. Right. Oh, and her mass is 52 kilograms. Okay. Okay, there we go. So that's what we were told. That's the setup. Okay. Now, the question is how much work was done lifting her up. So one way you could do this is you could say work is force dot distance. Okay. Now, the distance she's moving is definitely off on this weird 31-degree angle. So the force moving her up probably has something to do with her weight, right? Isn't it like lifting her against gravity? Okay. So the fact that those are at different angles, don't I have to consider like I have to throw in a cosine somewhere, right? Right. Maybe we could do work is equal the magnitude of force times the magnitude of the distance moved times the cosine of the angle between those two, right? Kind of like we did before. Okay. Now, force, could that be her weight? Guys, how much does she weigh? How many newtons?
500.
520 newtons, right? Is this right here? mg. So we're going to call that 520 newtons, right? Now that's a vertical type force, isn't it? Earth's pulling her down that much. This escalator is lifting her up against that, right? So think of this as being like vertical. Okay. Now the distance is off on this angle, so it's 227 meters distance. Okay. Now here's where you have to really think deeply and critically about this. Okay. As if you're lifting up against gravity, and we got this distance here, you guys see that the angle between those two is not the angle that they told you. It's actually this big old angle right here. You guys see that? Right. So when you get a force times distance problem or like some equation that involves like cosine of an angle, okay, be careful that the angle they give you is the angle that you're actually going to plug into the cosine. Because if you plug in 31 degrees here, you get a totally wrong answer. Okay. You need to play off this big angle right here. You guys, how many degrees is this? 59. You guys see it's 59 degrees? Because it's 90 degrees minus 31 is 59. Okay. That's the angle that feeds into here. That's the parallel components that are both going up. Okay. So I could say cosine of 59 degrees. Right. And that will give you the correct answer in joules, how much work was done lifting her. So it's 520 Newton weight, 227 meters distance, but cosine of 59 degrees between those two. Okay. So that's going to be 60,795 joules, or I could probably call that about 61 kilojoules. 61 kilojoules. Okay. Is that right? Okay. Now, another way you could have done this is you could say the work done lifting her is equal to the potential energy that she ends up with at the end of this escalator ride. Could be like that. Right. Okay, but now we know her mass, we know the gravity field, but we do have to solve for this height, right? So isn't this just straight trigonometry? If you know the length of the hypotenuse and you know this angle here, guys, this is 227 meters times what? So yeah, sine of 31 degrees. Because opposite of 31 degrees, right? Haven't we done like a million of these? Let's see, what is our actual height change for this full escalator ride? 227 meters distance. Sine of 31 degrees. We're looking at 116.9 meters, right? So she changes her elevation by that much, right? So that's the number that's gonna feed in right there. So the work done lifting her is 52 kilograms, 10 meters per second squared, times 116.9 meters, just like that. Okay. So 52 times 10 times 116.9. Of course, you guys already know what the answer is going to be. It's got to be like this. So looking at 60,788 joules, which again, I can call about 61 kilojoules. There you go. So it's the same thing. Okay, you guys good there? Okay, number 78. Oh, we're getting graph. Right, so have to throw some graph columns in here. Okay. We're looking at force versus displacement. That's what it says here, and that's what axis of the graph, force in newtons, displacement in meters. Okay. Calculate the work done to pull an object 7 meters, and then there's a follow-up question like what's the power in 2 seconds. And so first thing first. Now notice that this is a variable force. The force is always changing, isn't it? Right, which we haven't really dealt with so far. Like this escalator pulling this lady up the hill, or Diego pulling the sled, or pulling the refrigerator up. We're assuming like a constant force, right? But that's not true here. Right. So I wonder what property of this graph would tell you the answer to this question, how much work was done. Okay. See, if it was a constant force, when there should be like a constant line in this graph, right? And then how does the equation translate to the graph? Well, if work is force times distance, guys, force times distance, could that be like the height times the base, which would be like a rectangle, right? So guys, what property of this graph tells you work? So force versus distance. Is it a coordinate, a slope, or an area? Area. So the area under this curve, force versus distance, tells you the amount of work, right? The energy change. Okay. And the units are also consistent with that. Newtons times meters gives you some number of joules. And so that's what we want. Really, the way we're going to approach this is to find the area under the curve up to 7 meters. Now it's a little bit tricky because you need to chop off this graph a little bit. This is the 7 meter mark right here. You guys see that 7 meters ends right there. Right. So I see a little triangle right there. I see a tall, skinny trapezoid, which are going to break into a little rectangle on the top by a little skinny triangle, and a big old rectangle right there. And all we have to do is add those bits together and get the work done. So number 78. Okay. Let's go. Work is equal to. Okay. I'm going to add those 4 bits together. So starting with this triangle. Now, isn't the area of a triangle 1/2 base height? Let me get my voice plugged in here. 1/2 base height for area of a triangle. So let's go. Triangle is 1/2 times a base of 2 meters times a height of 20 newtons. Okay, so that's just this little bit right here, 1/2 base height for the triangle. Okay. Then next to this is, okay, tall skinny trapezoid. I'm going to break that into a little rectangle topped by a little skinny triangle. So this rectangle down here, is this a base of 1 meter and a height of 20 newtons? Is that 1 meter, 20 newtons? So I got 1 meter base and a 20 Newton tall rectangle. Okay. And on top of that is a skinny triangle. So 1/2 base height has a base of 1 meter and a height of, do you see, guys, what's 50 minus 20? Is that 30? 30 newtons? Just like that. Yeah. And then plus, right now, here's the big bit right here. Right. Going from 3 meters to 7 meters. Guys, what's 7 meters minus 3 meters? Yeah, 4 meters. Okay. So a rectangle with a base of 4 meters and a height of what? 50 newtons. You guys see 50 newtons? Is that true? Just like that? Okay. Okay, so let's add these 4 bits together. So the work done is equal to, let's see, I got 20 joules from the first bit, plus another 20 joules from the second bit, plus 15 joules from the third bit, plus 200 joules. Big old rectangle. That 255 joules. Maybe just like that. Okay. Guys good? And so that was question A. There's a follow-up question. It says, what is the power if this was all done in 2 seconds? 2 seconds. So isn't power the rate of work, which is work per unit time? So we're going to take 255 joules of work that all happens in 2 seconds. $127.5. Okay, and what is the unit? Watts. 127.5 watts. Watt is the unit.
What is the unit?
Let's got that.
Pretty good.
At number 81, a pulley system. Oh, pulley system. You guys were just setting up some pulley systems the other day. Okay. Lifts a big old weight, 1345 newtons, a distance of 0.75, 0.975 meters. So a little bit shy of a meter, right? A couple of centimeters short. Paul pulls a rope, distance of 3.9 meters, just a little bit short of 4 meters, right? Exerting a very small force of only 375 newtons. But you guys know these numbers are kind of work out this way, right? Because you guys did this yourselves, right? So the heavy weight lifts up just a little bit at a time. And on the pulling end, you're pulling lots and lots and lots of rope, but with a very small input force. But ideally, like force times distance should be the same on both ends. Okay. Well, we're going to see, because that's where we're getting these questions. What's the ideal mechanical advantage versus what's the actual mechanical advantage? And then finally, what's the efficiency of the system? Okay. So 81. Okay. You know what I want to do before we get chugging too far on this is draw some diagrams. Okay. Here, do you guys see? Let's calculate real fast the ideal mechanical advantage. 3.9 meters compared to 0.975 meters. Basically a 4-to-1 ratio. In fact, it is exactly a 4-to-1 ratio, isn't it? You see that? Okay, that's the answer to the first question, ideal mechanical advantage. Okay. Which matches here. When you guys were doing this lab a few days back, remember I left this on the projection screen the whole time, right? So I showed you guys here's the theory of why this works. And then ideal mechanical advantage is exactly what we just did. It's the ratios of the distances. So it's just based on the geometry. Okay. Now what we're eventually going to get to is the actual mechanical advantages is the ratio of the forces, right? Which should be pretty close to the same, but you know, if there's a little bit of friction going on, maybe not exactly. Okay. So then you can go one more step to calculate efficiency. Now, when you guys did this on your lab paper, I had you guys draw the diagram, calculate this, and calculate this. I didn't have you calculate efficiency. We'll do that today with this problem. So I cover that base too. Yeah, that too. Okay. Now I've graded everything that you guys have turned in so far, except for this lab, because I'm going through and drawing diagrams with you guys. So I think this is actually a really good opportunity to draw some of these diagrams again, because looks like that is a good opportunity you can get out of school that way. So we have a ceiling and a floor, or maybe it's like a beam up here, like that cross beam on your ring stands and the floor. Okay. Can you guys draw a 4-to-1 mechanical advantage pulley system? Let's see that. Okay. And I've set up 2 because there's multiple ways to do this. So I'll show you guys at least 2 answers. Can you set up a 4-to-1 mechanical advantage pulley system? 4-to-1. Okay. Give you guys a little head start right there. 4-to-1 mechanical advantage. You have some pieces within reaching distance here. Right? Got these pieces, single pulley, double pulleys. So one way that you could do this, I could take a couple of those single pulleys, I could fix them to either the ceiling or the that beam on the ring stand. Okay. Maybe I'll want a movable pulley down here. I'm gonna put the double pulley down here. Right, so this guy is this guy, right? Is that okay? This guy's right down here. All right, and then maybe, I gotta fix the weight to the double pulley. So it's thinking out here, I got a big old weight. Right, and I'm gonna take some pink ink and draw the string or the rope. Right, so I'll go from here. Let's get a little hook going on right there. Okay. Let's see, how could I do this? I could go underneath this double pulley. Okay, over this one. And go underneath the other double pulley. Over this one. And then bring it down this way. Then here's Paul. Right, just like that. Do you guys see now? Of course, it's only one rope, but you guys see 1, 2, 3, 4 strands going up. So it's not like this weight's been split into 4. All right. So however much this weighs, you should only be pulling down with a fourth of that force. He has a 4-to-1 mechanical advantage. You see that 4-to-1 mechanical advantage? Right. Maybe you drew that, or maybe you do something different. But you know what? One of the pieces that you guys had, I don't have it within reach right now. I think I put it back in the lab closet. It's a really funny looking pulley. It was like these 3 pulleys that were like different sizes, and they were all connected together. So it was like one giant piece. Okay. You could have used that to create a pretty fancy pulley system. So I'll treat that as a fixed pulley. I still need a movable pulley. I'm still going to use the double pulley setup. So that's this guy is right here, right? You guys get that? Okay. I'm going to fix the weight to the movable pulley, just like I did over here. Okay. And then break out some pink ink and start connecting some string. So let's go around this guy, up here, around this guy, up here, and then finally down here. And here's Paul. Okay. And yeah, do you guys see 1, 2, 3, 4 strands going up? So it's like a 4-to-1 mechanical advantage system too. So there you go. There's 2 different ways to do it. All right, you guys can draw that.
Why is there a third, much larger pulley?
Oh, just because it was one of the pieces. Yeah, so you don't actually need it for for the setup, but yeah, one of your pieces look like that. Yeah, maybe we'll take that out of lab closet in the future so you guys can see that again. All right, so that was a good exercise there. Okay. Now let's run the calculations that they asked for. So 81 part A, what is the ideal mechanical advantage? So mechanical advantage ideal is there. Now this is based on geometry. So it's the length that you pull divided by the height change of the weight. Okay. Here, let me see this down here. So that's 3.9 meters of rope that he's pulling. So he's pulling lots and lots and lots of rope. Okay. And this thing moves up just a little bit. 0.975 meters. Okay. I think this one is like exactly a 4-to-1 ratio. Can I just do that? Yeah, it's right there. So it's 4/1. Sometimes I write it this way with a colon, 4-to-1 mechanical advantage. Okay, 4-to-1. The actual mechanical advantage, I'll call it real, the real mechanical advantage, is the ratios of the forces. Force out over force in, or you can say weight divided by the input force. And that's going to be, this was a 1345 Newton weight. And he was applying a 375 Newton input force. So it looks like he's about 4 times as strong, right? But it might be a little bit less than that. Right? But we're going to find out. But it's 1345 over 375. It is less than that. It's like 3.59 to 1 ratio. So I can call it like 3.59 to 1, like mechanical advantage. You want to call it, right? Okay. So the strength only gets multiplied about 3.5 times because, you know, probably like some frictional forces and whatnot going on. Yeah, you know what? think this thing's out of juice too. All right, well, you guys can hear me. Ugh.
Goodbye, voice.
Okay, is that all right? Okay, and last part is what is the efficiency of the system? Efficiency. Okay, now I'll show you guys two different ways to do this. One way you can do this is exactly what I was showing on the on this projection screen the other day when while you guys were doing this lab. You just take the ratio of those perspectives on mechanical advantage. Right, just take the ratio. So part C, efficiency, is equal to, I could do the actual mechanical advantage compared to the ideal mechanical advantage. Okay, and that's 3.59 to 1 compared to 4 to 1. Right. Oh, let me say times 100% just to turn into a percentage. Times 100%. Percentages look nice, right? So what is that over 4? Okay, and I'm looking at 89.7%. Okay, so for every 100 joules of work he puts into the system on his end, there's only almost 90 joules that actually goes into lifting the object. Okay, the other goes to like frictional forces. Okay, okay. Maybe there's like a thermal change, like if you put a temperature on the pulleys, they'd warm up a little bit. We'll be okay. Okay. Now there's another way you could also calculate efficiency. By the way, a common symbol for efficiency is Greek letter eta. Looks like an N with an extended leg on it. So efficiency equals. Okay. So here's another way. You could do work out compared to work in, which is like force times. Or maybe I should say weight times height. Weight times height compared to input force times the length of the rope pulled. Right. So this was a 1345 Newton weight, 1345 newtons. It was lifted a height of 0.975 meters. He was inputting a force of 375 newtons. But he pulled lots of rope. He pulled 3.9 meters of rope. Yeah, I'll say times 100%. Keep it consistent with what we did before. So 1345 times 0.975 divided by 375 by 3.9. Okay. And oh, that's the exact same thing as I got before. 89.7% efficient. Okay, so there you go. There's 2 paths through the forest to get to the same answer. Guys good? So that's chapter 10. I'll switch over to chapter 11. Right. And we won't do all these because we're running out of time, but we can do probably at least 2, maybe 3. Okay, number 57. Tony has a mass of 45 kilograms and is moving with the speed of 10 meters per second. Find his kinetic energy. Oh, so that's just straight off this list right here, isn't it? Kinetic energy, 1/2 mv squared. So that's real plug and chug. I think we can do that. 57. Kinetic energy, 1/2 mv squared. It's got a mass of 45 kilograms. Got a speed of 10 meters per second. Square the speed. I'm looking at 2250 joules of energy. Okay. All right, that was question A. Question B, suppose the speed changes to only 5 meters per second. Now what is this kinetic energy? Okay. So 1/2 mass speed squared. See what it's going to be. So 1/2 45 5 squared. Now before I hit enter, okay, I want you guys to tell me. I think you guys can figure this out. He has half the speed, right? So what is this new kinetic energy going to be compared to his old kinetic energy? What ratio? 1/4. Ah, it should be 1/4, right? A fourth of 2,000, it should be a little over 500, I think, something like that. Okay, because you guys know a factor of 1/2 squared is a quarter, right? Talked about this before, right? Yeah, 562.5 joules. Right, half the speed, a quarter of the kinetic energy. Okay. And then question C was, what is the ratio of those two kinetic energies and why? So it calls Ka, calls Kb. So Kb compared to Ka, 562.5 joules compared to 2250 joules is a 1-to-4 ratio. Okay. And you might want to like write a sentence explanation, but at the heart of it is some version of this. Kinetic energy is proportional to the square of the speed, right? So if you have half the speed, 1/2 squared is 1/4, you end up with a quarter of the kinetic energy. Okay. Oh, remember we were talking about this with like a car braking to a stop. We sort of did the reverse. We said, well, what if you double your speed? It's like going from B to A, right? If you double your speed, double square is like 4 times the kinetic energy. And it's going to translate to like 4 times the braking distance. Okay, if you double your speed. Okay. Which is looks like the next setup. Number 60, a car brakes to a stop. So a 14,700 Newton car. Notice they told you the weight of the car, not the mass. So there's going to be one extra step to throw in there to get the mass. Okay. Okay, traveling at 25 meters per second. The brakes are applied. The car comes to a stop. And the average braking force is 7,100 newtons. How far will the car slide? Right. All right. So the way they ask this question is pretty plug and chug. So I've got an open system. I'll just set that up and solve it with you guys. But just think it's more interesting like proportion type questions you can ask too. So we'll look at some other questions. Okay. Let's get the mass of this car. Guys, is mass equal to weight divided by gravity field? Right? That'd be true, right? Okay. So let's take 14,700 newtons weight and divide by 10 meters per second squared. Couldn't that be mass of 1,470 kilograms? Not exactly, pretty close to, right? Right. Well, we're gonna say we have a mass of 1470 kilograms. How far will the car slide? Okay. So I'm gonna do an open system, sum of energy initial plus or minus the work done is equal to sum of energy final. Right? And the initial energy is all kinetic, 1/2 mv squared. So subscript not. Okay. And the work done is, well, the work done by friction. So I'm going to subtract, taking energy out of the system, the friction force times the distance. And then I'm going to end up with 0 mechanical energy. Right? There's no kinetic because it's brake to a stop. There's no potential because it hasn't gone up any hills or anything. Okay. Right. And the question is, what is this right here? What's this braking distance? Okay. So 1/2. Okay. Now mass. This is what we did all this mass stuff for. Okay. 1470 kilograms times the speed of 25 meters per second being squared. Okay. Hey, can I slip in an algebra step here? Take this and add it over here. Okay. Is equal to the braking force of 7,100 newtons times the braking distance. Is that okay? Okay. So the distance the car brakes is 1/2 1470 kilograms, 25 meters per second being squared, all divided by 7,100 newtons. Right? Just like that. So 1/2 1470. So I'm getting a braking distance of 64.7 meters. About 65 meters. Okay. Okay, all good. So again, I really like this as a classic setup because classic question is like, what if this guy doubled the speed to 50 meters per second? What would happen to the braking distance? Be like 4 times, right? Factor 2 squares like 4 times. Okay. There's one more question I want to do with this car braking to stop. What is the coefficient of friction between the tires and the road? I find here you go, this blank page. is this coefficient of friction force compared to the normal force? It's the truth is kinetic friction. And if it's static friction, well, it has to be at least as big as whatever this ratio is. So we'll just say equals and solve that way. They told you the friction force, 7,100 newtons. Friction force. Okay. Now the normal force. Wouldn't that just match the weight of the car? Whatever the weight of the car is, isn't the road holding up with that amount of force? They told you was 14,700 newtons. Okay. So coefficient of friction, either kinetic friction or minimum static friction, one or the other, is like 0.48. Now, I remember taking traffic course back in college and seeing some of these coefficient of friction between tires of road. If you have like new tires, dry road, this number can get a lot higher. It can get closer to 1. In fact, it's possible to get a little bit bigger than 1, which means it'd be actually easier to lift a car than it would be to push it or to break it. Right. So look at this coefficient of friction. Maybe the road's like wet or something like that, so it's not exactly ideal conditions, but that's what got going in there. All right, so that's my own side question. But that is a great pause point right there. So we still got 3 left to do, but we'll save this another day. Tomorrow's gonna be a lab day. The lab tomorrow. You guys have a great afternoon.